Oui, je connais les gens, je ne vais pas a lot of things, but at the end of the day. We have to sign something. No. No.
Sécurité, il va le voir. Vincent est présent.
Okay, good morning. Mr. William PENSEC, today is the day of your PhD defense. I am Jean-Max Tutert from Cette, and I'm very pleased to be the chair of your defense jury. I will give the name of the members of your jury. Then we will start. You will have 45 minutes to present your work, and then there will be the question session. So you had three reporters in your jury. Professor Vincent Béroul from Université Grenoble, which will take part in this jury remotely. Professor Laila Bettina from Warburg University. Professor Nelly Mettens for Leiden University, Catholic University 11. Dr. Francesco Regazzoni, who is head of research at the University of Amsterdam and at the Università della Svizzera Italiana in Switzerland. Your thesis director, Professor Guy Gonia from University Bretagne Sud, and your PhD co-director, Dr. Vianney Laporte, also from University Bretagne Sud. Okay, if you're okay, we can start.
Hello everyone, thank you, Mr. President, for the introduction. So I will present to you my work about entitled NS Processor Defense Against Physical and Software Threats by Securing DIFT Against Faultination Attacks. I will present you all the terms in the beginning of this presentation. At first, the context of this PhD is Internet of Things. Internet of Things, IoT, is some devices with a wide range of application ranging from smart agriculture to smart homes. This device has a rapid, increasingly growing. The market is growing rapidly, and all these objects relies on sensors depending on their application. For example, smart agriculture will use different sensors than smart homes. And what they have in common, all these objects, is they collect and share data. This data can be sensitive. And for that, they are increasingly vulnerable to multiple threats. Which threats? From the figure 2 below, these data are coming from Bitdefender. As you can see, there is different categories of threats for IoT devices. They can be grouped as three main categories, which are network threats, with, for example, man in the middle, jamming, denial of service, and so on. There is also software threats with memory overflow attacks, code execution, SQL injection, and so on. And finally, hardware threats with reverse engineering, side channel attacks, and also fault injection attacks. These attacks can be dependent on different other threats. For my PhD, we will focus only on software threats and hardware threats with a focus only on fault injection attacks. I will present why after. To protect a system against IoT system against software threats, there is a mechanism called Dynamic Information Flow Tracking, for DIFT. It's a security mechanism that helps to protect against software attacks like buffer overflow, format string, and SQL injections. And as you can remember, these attacks are the same than the previous slide. And what they have in common, all these DIFT follow a security policy that detects them how to behave against different operations. How do they work? They have three different steps. The first step is the tag initialization. So there is different data into the system, and for example, D1, D2, and D3, and the DIFT mechanism will attach one tag to each data. For example, in my case, in this case, green tags are trusted, while red tags are untrusted data. The second step is the tag propagation. So this time, the data is fetched into the processor, and it will be computed under different operations, different functions, and in parallel, the tag associated to this data is fetched and will be computed according to the security policy of tag propagation. Finally, the last step is tag check. This step represents, before the results of the computation, the tag associated to the result. Before writing the data into the memory, the tag associated to the result is compared with the security policy. And so the tag is compared. And if there is a violation of the security policy, then the DIFT could maybe, for example, raise an exception and stop the application. For example, in this case here, we mixed D2 and D3 value to form D4 data. The tags of D2 and D3 form the tag of D4. And as D2 is untrusted and D4 is trusted, we could imagine that D2 is coming from a user, from an input source, while D3 is a system data. And maybe the DIFT will deny the mixing of these two applications, of these two data. And so D4 would raise an exception thanks to this DIFT mechanism. For DIFTs, for hardware DIFTs implementation, there is three main approaches. The first one is off-core approach. So you have one core dedicated to the execution of the application, and in parallel, you have a DIFT coprocessor that will compute all DIFT operations. The main advantage of this approach is that it requires no internal hardware modifications to the main core. But on the other hand, it needs support from the OS for the synchronization between the tag and the data. The second approach is offloading cores. So this time, you use a multi-core CPU. And one of these cores inside this multi-core CPU is dedicated to the execution of an application. And another core is dedicated for the DIFT operations. The advantage is that the hardware does not need to know DIFT tags and policies, and no synchronization is needed. On the other hand, as the biggest disadvantage is that it requires a multi-core CPU, and it reduces the number of cores available because it takes one core for the application and one core for the dynamic for the DIFT operations, and so increase the power consumption. The last approach is in-core DIFT. So this time, the DIFT operations are inserted directly inside the main core, in parallel of the data. So the advantage is that you do not need multi-core CPU, you do not need synchronization between tags and data, because they are processed in parallel, and so there is very low performances overhead. On the other hand, it requires highly invasive modification of internal hardware for tag computations and storing. So in my case, we will work on an in-core dynamic information flow tracking. So dynamic information flow tracking can protect efficiently a system against software attacks, but what would happen if this DIFT is disturbed? Or if we consider a tag, what happens if the tag is modified? And to disturb a bit or a register inside a processor, we can use faultiation attacks. Faultiation attacks involve introducing on purpose one or more faults into a system to disturb its behavior. There are several ways of injecting faults, for example, clock glitches, voltage glitches, laser, electromagnetic fault injection, etc. And the precision may vary depending on the category used. For example, if you use clock glitches, the effect will be on the whole circuit, while if you use laser, the effect will be more local. You will be able to fault one register, one bit inside the register. And there is numerous studies in the literature that show that there is vulnerabilities led by faultiation attacks into critical systems. For example, to only cite these three, with some manipulation of the power supply, they have been able to control the program counter on an ARM device. With electromagnetic faultiation attacks, some have been able to recover an iOS key by targeting the cache hierarchy and the MMU. And finally, with the laser fault injection, they have been able to allow the replay of instruction on a 32-bit microcontroller. There is plenty of these studies into the literature, but none of them have shown the vulnerabilities of DIFT against faultiation attacks. And this is why we are working on that for my PhD. So the research challenge from this introduction is how can we maintain maximum protection against software attacks in the presence of physical attacks? Our objective to answer this question is to provide a robust security mechanism against software and physical threats. And for that, we will propose lightweight countermeasures against faultiation attacks, targeting constrained systems such as IoT. And for this countermeasure, we will take into account constraints such as efficiency, area, and performances overhead. The outline of this presentation will be as follows. At first, I will present you the de-risky dynamic DIFT design, which I'm working on, and a vulnerability assessment of this design. Secondly, I will present you a tool that I developed for my PhD, which name is Fault Injection Simulation for Security Assessment, FISA. Third, in the third section, I will present you the countermeasure I'm proposing against faultiation attacks. And in the fourth section, I will present you the results of this evaluation. Then, in the last section, I will conclude this talk and draw some perspectives. So, at first, the DIFT design. So, it's a DIFT design called de-risky. It's made by researchers at Columbia University in the USA in partnership with Politecnico di Torino in Italy. It is based on the 32-bit RISC-V processor RISC-V of Perl platform, and it is open source. You have the link here below. Also, this DIFT considers a 1-bit tag data path inside the CPU. And one of the main advantages, it has a flexible security policy that can be modified at runtime. This figure shows you the architecture of this de-risky. In red, you have the different DFT operations, the DFT steps. For example, the tag update for the tag initialization or the tag update, then the tag propagation and the tag check. Also, you can note that there is different modules that have been extended with tags, for example, the PC, the register file, and the data memory. And finally, you can note two different registers inside the CSR, which are TPR for tag propagation register and TCR for tag check register. These two registers store the security policy of this DIFT. So I did a vulnerability assessment of this DIFT and to check, of course, if this DIFT is vulnerable against fortification attacks. And if it is, to determine the spatial and temporal locations of the vulnerabilities. So this vulnerability assessment has been presented in Sensor SMP 2023. So for this vulnerability assessment, we consider an attacker able to perform a physical attack to defeat the DFT mechanism and realize a software attack. For that, he will inject faults in DFT-related registers, and these faults are bit set, bit reset, and bit flip. We consider these three faults models because they are at bit level, and the majority of our registers inside the DFT is on 1 bit. The methodology used is we analyze 3 use cases: a buffer overflow attack, a format string attack, and a home-made case called compare compute. For each of these use cases, we do a temporal and logical analysis of the tag propagation. And due to time constraints, I will only present you one use case in this presentation, which is the buffer overflow. So to present you this case, at first, the attacker exploits the buffer overflow to access the return address register and perform a ROP attack for a return-oriented programming attack. So at first, the attacker has a source buffer initialized with some data, and inside this source buffer, there is at the last index an address. It is this address that the attacker wants to access and execute. Because it is manipulated by the user, the DFT has tagged all this source buffer as untrusted. And there is also a destination buffer inside the stack memory, which is trusted for now. There is also the return address and register and the PC. In the second step, the source buffer is copied into the destination buffer. So thanks to the DFT propagation security, the tags associated to the source buffer are copied into the destination buffer. And so, as the source buffer is bigger than the destination buffer, an overflow will happen. And this time, the address stored at the last index of the source buffer will overwrite the return address register. And so now the stack memory has taken all the tags from the source buffer, and so now the stack memory is untrusted. Once the function ends, the return address register is loaded into the PC, and so the tag associated with the return address is also loaded into the PC. So now the PC is untrusted, which means that in the final step, when the PC address is fetched to be accessed, the tag will be also fetched in parallel of the PC address. And thanks to the DFT mechanism, because the security policy denies the execution of a PC untrusted, an exception will be raised and the application will be stopped to avoid this ROP attack. To represent this attack from the moment of when the tag is fetched, I did a temporal analysis of the tag propagation. So the cycle 3430 represents the moment of when the tag is fetched from the register file and processed into the pipeline of the processor. And as you can see, it takes 3 cycles before the tag is compared with the security policy. And in this last cycle, the security policy is compared with the tag, and so the violation is detected, and so an exception is raised. This figure shows that the attacker has 3 cycles to inject a fault into this processor to defeat the DIFT and bypass the security mechanism. But, so this figure shows that, but it does not provide an overview on the different registers used in this propagation. And for that, I did a logical and spatial analysis, which is represented by this figure. In red below, you have the exception signal that we consider that if this signal goes from 0 to 1, the exception is raised and we cannot stop it. So we want always, from the attacker point of view, this signal should always stay at 0. In yellow, also, there is the different register used in this propagation. And in blue, this is all the signals. As you can see in this figure, if an attacker is able to perform a fault injection, for example, into the register file type, the fault will be propagated into the first AND gate, and due to the AND gate, to the AND logic, it will be propagated into the second, the third, the fourth, and the fifth. And so the exception will be bypassed. So the exception will not be raised. So this figure provides an overview on the different registers the attacker has to inject a fault to perform a fault injection. And now to confirm these results, we did a logical fault injection simulation campaign to verify that. So all faults are injected into the HDL code at SQL accurate and bit accurate level. We focus on all 55 DFT related registers, and a reference simulation is done at first without any fault. The results of this campaign is classed in 4 groups. The first group is a crash, a silent fault, a delay, which means that the exception has been raised before or after the reference simulation, and a success, which means for us, it's an attacker point of view, and it means that the DFT has been bypassed. All simulation has been done with QuestaSim 10.6e, and we use FISA, which is presented in the next section, to automate our injection campaign. The results of this vulnerability assessment on the buffer overflow use case provided 24 successes out of the 1,422 simulations. These successes are distributed from this table, as you can see on table 2. This table 2 can be read from, for example, if you want to inject a fault to bypass the DFT, and if you consider only PC IFO type register, you will have to take into account only a bit reset or a bit flip fault model, and to perform a fault injection at cycle 3431 only. To summarize this campaign, on all 3 use cases, we got 95 successes out of the 4,466 simulations. This campaign showed us 43 highly sensitive registers on the 55 related registers, and we have shown that this de-risky DFT is vulnerable against fault injection attacks. And the propagation of fault is facilitated by paths fully made of AND gates. So this shows us the registers that will be protected in priority to protect the system against these faults. Now the second section, the tool. It's so FISA, it's an open source tool. The link will be provided later in the presentation. It allows the CPU designer to analyze throughout the design cycle the sensibility against fault injection attacks. And it's integrated around an HDL simulator, which is only for now QuestaSim. All the generated results can help to find vulnerabilities during the design phase, and so it enables the principle of security by design. And this tool has been presented in DSD 2024. So this figure presents the software architecture of FISA, and FISA is mainly 2 main classes and 1 HDL simulator in the middle. So at first, the first class, the TCN generator, will take into account, it will take into input 2 files, which are the target files, which contain all, for example, registers, signals, gates, or whatever the designer wants to assess, and also a config file in JSON format, which will contain, for example, the fault model, the application, the the attack window, and so on. And so the TCL generator will process these two files, and from these files will generate a batch of TCL scripts. Then QuestaSim, the HDL simulator, will be able to take into account a design from HDL files, so system Verilog, and VHDL, for example, files. Also, will take an application from a memory init file in .mem, and will execute each simulations contained into the TCL scripts. Each simulation will provide a log, which will be stored into a log files in JSON format. And then the analyzer, the last class, will be able to process all these log files and generate the results in two different formats, which are LaTeX tables and also heatmaps in PDF format. These two results will be presented to you in the fourth section of this presentation. Also, FISA supports 7 false models for now, which are from the literature, from simple ones like set to 0, set to 1, and single bit flip, to more complex ones where we inject multi-bit faults in 2 targets at the same time. And all these false models are used in this PhD. Now, the countermeasure I'm proposing to protect against fault injection attacks. So there is different ways of protecting a system. The first one is hardware redundancy, which, for example, duplication of the circuit to compare the results obtained and check for any difference. Also, there is a temporal redundancy, which means that we will repeat operations in reverse to compare the result with the initial value. The third solution is, for example, replay instruction, where we will execute multiple times the same instruction or block of instructions. And also there is the obfuscation, which will add dummy cycles into the process, and for example also shuffling the data into the process. Finally, there is also information redundancy, where we will add additional data to the information to detect or correct the initial value. This countermeasure is also known as error detecting or correcting codes, and represent, for example, simple parity code, AMI code, BCH, Reed-Solomon, and so on and so on. And for my PhD, we will focus on information redundancy. Because, I will explain why. And so on information redundancy code, we will focus on simple parity, AMI code, and a modified version of AMI code called SecDed for single error correction, double error detection. So this information redundancy codes only adds a few bits to detect and correct a potential error. And so there is a very small overhead on area and performances. So this implementation of AMI code and simple parity has been presented at ESV LSI 2024. So to present you how simple parity works, so simple parity is often used for error detection only. It adds an extra bit for parity computation, so P0 in this figure 13, and this P0 parity bit will compute the parity from D0 to D6 in this figure, all the message. The second countermeasure is AMI code. It's a linear error correcting code invented by Richard W. Hemming in 1950. It is mostly used in digital communication and data storage systems, and it is able to detect and correct single-bit errors. For that, it uses redundancy bits that are placed in power of 2 positions, as you can see on the figure 14 at your right. This figure shows R0, N1, R2, and R3 redundancy bits, and these redundancy bits are computed according to the equation 1 at your left. As you can see on this equation, each data bits are being protected by at least 2 redundancy bits. For example, D0 is protected by R0 and R1, while if we consider D6, it is protected by R0, R1, and also R3. The third countermeasure is SecDed. So it is based on AMI code to detect 2-bit errors and correct single bit errors. And for that, it's a mix between Amicode and triple parity, because in the sense of it uses Amicode and only add one extra bit for the parity computation of the whole message. So in this figure, the figure 15, the effective registers. Then a decoder will take the value of the register and compare them with, will compute the redundancy, the parity of this register, and compare them with the registers associated. And so if one error is detected, Amicode will be able to correct it. So the correction will be sent into the pipeline, but also will be sent in reverse to correct the faulted registers. In the case of there is no new value as input, of course. In the second case, there is two faults that has been detected thanks to SecDev. This time, there is no output corrected, nothing is emitted, but this time an error signal is emitted to provide the user, for example, that two error has been detected, to provide to the user, to the system, or whatever, that two errors has been detected. And so it is from the developer to implement the reaction of these two faults. A second implementation is to use multiple registers on one encoder. So this time you take, for example, n registers, and you take the n inputs, and these inputs are sent into the encoder, which will process again the redundancy, the parity bits, and all the process is the same than the previous implementation. So I will not provide the explanation again. The third solution, in my case, is the protection of the register file tag. It's a special case because the register file tag has two white ports. And so to avoid having a bigger array overhead due to the implementation of a third white port, we decided to wait for one white port to be available before writing the correction inside the correct register. So this is the only difference. All the same is all the rest is the same than the previous implementations. And the last example is splitting one register on multiple encoders. So this time, for example, in this figure, you can see an input on 2 bits, and these 2 bits are split into 2 encoders. So each encoder will compute the parity, the redundancy of each bit, of each 1 bit of this input. It means that if an attacker is able to perform a falsification on the 2 bits, because it is protected by 2 encoders, the Amicode will be able to detect 1 bit, 1 fault, and not SecDev for 2 faults, because each bit is separated. So each bit will be corrected, and so the full method will be recovered. And so it was like no fault happened. So from this implementation, we decided to evaluate different group compositions. And for that, so different implementation strategies can be applied depending on protection requirements. And depending on the protection, the efficiency will vary. And so in my case, of course, we would like the best protection at the lowest cost possible against different fault models. So the different group composition and the different strategies I'm proposing are this one. The first one is a minimization of groups to minimize the array overhead. The second strategy is a protection by stage, which means we will protect each stage of the processor, and we consider 7 stages for the de-risking. These stages are instruction fetch, instruction decode, the execute stage, the register file tag, the LSU, and finally the 2 registers inside the CSR for the tag propagation and the tag check policy, which are highly critical. The third strategy is a protection by register. So this time we protect each register individually. The fourth strategy is the same as the previous one, but this time we split the CSR, the two CSR registers, by group of operations. And the last strategy, the strategy 5, we couple split registers. So it means that we split each register and we couple each bit to another register. This can be represented with this figure. So for example, we take a big register with 4 bits, R0 on 4 bits, and we split each bit on one encoder. Then we take some other registers and we couple 1 bit of each register to these 4 encoders. Then AMICODE and SECDED will be able to process the redundancy bits, the parity bits, and then it means that if the attacker is able to perform a fault on the 4 bits of R0, because the 4 bits are split, the 4 bits can be recovered thanks to the decoder. So from these different group strategies, we decided to evaluate them. And so I will provide in this section the results of these experimental results. So we use FISA for fault injection campaigns, and we consider more complex fault models such as multi-bit faults and multi-single bit faults. We again inject fault into DIFT related registers and also inside the protection related registers. We consider 4 fault models, which are single bit flip in 2 registers and single bit flip in 2 registers at 1 or 2 or 1 clock cycle, and multi-bit faults in 1 register or in 2 registers at 1 clock cycle. For the last 2 fault models, we consider only registers from 1 to 10 bits only to avoid having to simulate a large number of simulations. For example, if we consider using the full campaign for the last fault model, we would have to simulate 2 power 32 multiplied by 2 power 32 simulation for only the 2 biggest registers, which will take around 1 million years. So in this presentation, I will present you only the second and fourth fault model. In terms of FPGA implementation results, I did this implementation on Vivado 2023.2 using a Z-board Zinc 7000. And the first line of this table shows the implementation of the base processor, the de-risky, without any protection. As you can see, the different countermeasure or strategy of implementation, simple parity, AMICODE, and SECDED, do not exceed 7.55% of LUT overhead, and in terms of flip-flop, it does not exceed 3.98%. For the maximum frequency, there is no change, which means that there is no major impact on hardware and performances, and so the choice of the strategy and the countermeasure will not be on the hardware and performances overhead, but only on the efficiency of the security. To present you the results of this efficiency, this is the result from the first fault model, which is, to remind you, single bit flip in 2 registers at 1 clock cycle. The buffer overflow use case without any protection led to 1,406 successes out of the 48,000 simulations. And as you can see, with the simple parity, we can decrease this number to 0.46%, which is really good. And with AMICODE strategy 1, we go higher with 0.66%. It is explained because as we fault 2 registers at the same time, AMICODE is not able to process these 2 faults, and so we try to correct 1 fault, and so in general it will allow the injection of a 3rd fault, and so will lead to more successes than simple parity. But from the other strategies, the results are going down, and with SECDED, the 5 strategies, we got 0 successes because SECDED is able to correct, to detect, to correct the 2 faults. So this shows the fault model. So these 5 strategies of SECDED are really good against this fault model, which is logical. But what would happen if we consider a more complex fault model? For example, an exhaustive multi-bit fault in 2 registers at 1 clock cycle. So this time, considering again with the buffer overflow, without any protection, we got 450 successes out of the 68,000 simulations. And with a simple parity, we got only 59% of 59 successes, which is as a success rate 0.08%. This is a really good result because it's one of the best among them. And the problem with simple parity is that it only detects the fault and it is not able to recover. So this implementation of simple parity will lead to stop of the application, and so the application will not be able to process any further into the when the fault is injected. While, for example, now with Unicode strategy 2, it led to the worst success rate of this fault model with 1.33% of all simulations. And again, this is because we inject more faults than Unicode is able to recover, and so we will inject more faults, another fault that will be able to cause a success from the attacker point of view. Finally, we can see that from the results, the 2 best strategies are SecDet4 and SecDet5, and there is a small advantage in this case for SecDet5, but if we consider the 3 use cases, SecDet5 is way better than the others. And this is because there is a split of the different registers on different encoders. So when we inject a fault into one register, because it is split, the fault is recovered from each bit and each encoders. So this is, we can represent these successes out of this figure. You do not have to read in detail this figure at all. What is important from this figure is to see that there is 2 lines and 3 columns from this figure. And as each box represents a couple between 2 registers, this means that there is, for the unprotected version that we got 450 successes, there is only 5 registers which are highly critical. And the value in this figure are going from 1 to 32. And so there is a few results, a few successes which are distributed. And so now if we compare, this figure to Unicode strategy 2, which was the worst strategy in terms of successes, with, to remind you, 4,456 successes. This time, we do not have only 5 registers, but 7, with 2 columns and 5 lines. And the results inside each box is way higher, from 1 to 340. And if you are the main registers critical are the registers inserted with Unicode, the protection registers, which are not protected, and so we can lead to faults. Now, if we consider the best strategy, Unicode strategy, SecDet strategy 5, we got only 66 successes. And this time, you can see there is only 1 line on the top of this figure, and the results are going from 1 to 31 successes. And this time, these successes are coming from mainly the protection register of the register file tag, because it is not protected. But if we would consider a better implementation, we would lower this results number. Now, in terms of conclusion and perspectives, to remind you, the research challenge of this presentation was how can we maintain maximum protection against software attacks in the presence of physical attacks. I presented a vulnerability assessment of a DIFT mechanism against fault-injection attacks. And we have shown that this DIFT is vulnerable, considering different fault models from simple ones to more complex ones to defeat its DIFT and its protections. Secondly, I presented an open source tool to help find vulnerabilities during the conceptual phase, and it enables the concept of security by design. Finally, I'm proposing 3 lightweight countermeasures based on parity codes with an area of error smaller than 8% and no impact on performances. And these countermeasures show good efficiency in terms of security. Now, in terms of perspective, at short terms, I would like to propose more robust countermeasures to protect multiple faults. For that, I would like to evaluate Reed-Solomon, BCH code, or event replication to compare the results from this countermeasure to our actual proposed solutions. So this countermeasure will be evaluated in terms of area and performances override and security, of course. Also, I would like to further develop FISA to better integrate, to have a better integration in the design workflow. Also, support more fault models and having a more configurability. For example, having an automatization for finding targets into the CPU. Finally, I would like maybe adding a graphical user interface to provide a better user experience. At long terms, I would like to conduct real-world fault injection attacks. For example, we would consider cloud glitches with chip whisperer, electromagnetic fault injection attacks with chip shooter, and maybe laser for the different models I'm considering. For example, I'm setting alpha nav laser with 2 or 4 spots. And I would like also to extend the assessment of more complex DIFT. For example, Raksha from the state of the art, which consider 4 bits tied into the data path. And I would like to evaluate our proposed protection for this kind of DFTs and compare them with other protections to compare the different results. This research has led to different publications. So I got the Best Paper Award in Sensor SMP for the vulnerability assessment of the de-risked DFT. I also presented my work at the SVLSI for the implementation of Omicode and simple parity. And FISA has been presented at DSD 2024. FISA is also available at this link below on the slide on my GitHub. And also last year I had the chance to participate in a science outreach event called Ma thèse en 180 secondes in Rennes in March 2023. And the link is provided there on YouTube. So thank you for your attention. And now if you have any question, feel free to ask them now in English or in French, as you prefer. Thank you very much.
So thank you very much. We will start now the question session, and we'll start with Professor Leila Chetina. Please, Leila, and ask your question.
Thank you. Thanks for your nice presentation and a detailed overview of your work, which was quite extended and with some impressive results, but of course I still have some questions. So my first question is about your PISA tool, my SSA. I also have it for the reporting based on your thesis. So the comparison in table 4.1, when you compare with various solutions together, also formal methods, simulations, and all. So this actually should be maybe further refined. So could you comment on that? Why did you put all that together?
Yeah, the table for 4.1, I only did a comparison between the main methods of fault injection campaigns with formal method simulation and actual fault injection attacks. I did not specific evaluation on different tools because there is a lot of tools, but mainly what I can say is, for example, formal methods tools are how can I say this is difficult to use formal methods, tools for large design, for very big design, and it will take a lot of time to simulate, and there is some limitation also with formal methods due to, for example, design complexity. If, for example, if there is some loops inside the design, there can be some problems, some issues with that. And actual fortification attacks, there is different ways, and the problem is that you need a prototype of your design. So the design should already be finished before having the possibility of assessing it. So this is why I did in simulations, because you are able to do that during the design phase and be able to compare it during the design phase for finding the different vulnerabilities.
And you can still combine it later, right?
And of course, once the design is complete, you can, of course, do actual fortification attacks to prove your results.
Okay. And my second question is about your implementation results from Xilinx Zinc 7000 board, which, like, thinking about the IoT use case you talk about, does not really fit, at least not in my mind. Maybe there are boards that would then justify, but what's the kind of the argument behind?
Yeah, as you said in your report, this implementation were made only to compare the different results and not to having an overview on the number of clicks it will take on a device, but only to compare them in different results without having some constraints such as the size of the board. So
it doesn't actually give enough information about feasibility, right? It's just comparing with other existing approaches. So maybe that's something to look into.
Yeah, sure.
If you want to make argument for IoT use cases, I think it's a nice way to try it also on a more IoT-friendly platform. Right?
Okay.
Okay, could you go to slide 26? And I will first discuss the success with the DIFT approach. Yes, success 24 of 1422, and then later in the conclusions you say that the fault injection on that the DIFT is on Iris 5 is vulnerable to FIA with this number of 24.
Yeah, from
so what does it mean? Do you need 24, or is it the least you need, or is one enough? Is one too many? Could you argue exactly that?
As if you consider an attacker able to perform one fault, one precise fault, it only needs one fault to bypass the DIFT and succeed in its software attack. So you only need one, and this is why 24 represents a large number of successes, and so you have to protect them to have the lowest possible amount. Of course, the best would be to have 0 successes.
Yeah, of course, but with the percentage given, you're kind of still giving a suggestion on how to do that. Yes, I see. And can I have one more question? Yeah.
Oh yes, please.
Yes. So slide, I think it's 55, where you have conclusions, more like
55.
Looking 55. Yes. When you talk about what you would and could do next. So I looked at this evaluation, different codes, and then that immediately made me think of code-based post-quantum crypto systems, for example.
Yes.
Would that be something?
I don't really know post-quantum cryptography.
But you know that there are post-quantum crypto systems based on codes? Mechanism, for example, and
no,
okay.
Sorry.
Yeah, that's definitely something that kind of immediately caught my attention, because, as you know, it's like very, very hip at the moment, and it's a big thing, because of the fear of quantum computers. So that would kind of be really nice, because the work on fault injection and side channels in this respect is very valuable at the moment.
Yeah. It could be a perspective then.
Yes.
To implement.
Thank you.
Thank you.
Thank you very much.
Now it will be the turn of Professor Nelly for our questions. Yeah, okay, thanks. So thank you for the nice presentation that gave a very nice overview of your thesis. My first question is related to how realistic it is to inject the faults that you simulate. Because you have a simulator where you assume, okay, I can flip this bit,
Exactly.
for example,
Yes.
or I can flip these 10 bits.
Yes.
So you already mentioned it, I think, on the next slide, that you would like to perform real-world fault injection attacks. But can you reflect a bit on how realistic you think it is to inject the faults that you inject in your, or that you assume are injected in your simulator?
Yeah. If we consider different ways of injecting faults, for my fault model, as I said, the better one would be laser, because clock glitches is too global on the circuit, so it would not be precise at all. Electromagnetic fluctuation attacks can maybe be good for injecting fault, but laser would be the most precise. And it has been shown in the literature that it is possible to inject fault in precise registers at different precise time using a laser. And this is why I'm citing Elfenov laser, because I know that, I think this is this citation, this reference, but there is 2 and 4 spots. And so with my fault model where I inject 2 faults at the same time, it will be possible with this kind of laser. So this is realistic, but of course you need an evaluation of the board, of the circuit before injecting the real fault.
And then maybe as a follow-up question, because you assume that you can do laser fault injection, you focused on the DIFT related registers now.
Yes.
If you can use laser fault injection, would there be other vulnerable spots in the architecture? Assume you have already applied your countermeasures to all the registers and those are effective. Can you do other things still to disturb the system?
Yes, of course. You could fault, for example, the instructions. If you are able to inject a fault inside the whole circuit and not only the DFT, you could fault the instructions from the fetch stage or decode stage. You could fault also the data. Even if it's protected, there will be probably still some successes, some vulnerabilities somewhere, but you will have to evaluate the board to find them.
Okay. And then with respect to the evaluation that you did, so you compared for all the countermeasures, you compared against the unprotected case, of course, in terms of the FPGA resources and also the clock frequency, which then has an impact, of course, on the execution time. Yes, this, for example. But in IoT use cases, energy consumption is also important. If you would have to make a comparison of the energy consumption as well, how would you approach that experiment?
I know that some tools provide the possibility of evaluate the power consumption. I think Vivado can do it, but it gives an overview of this power consumption. The best one would be to implement it into a board and compare the real results.
Yeah.
But as the frequency is not really changed and the impact on area is very small, to not say no impact, because I'm only taking the main core. I'm not taking the whole SOC, because for example, in the article of the de-risky, they have shown that they have an overhead of 0.86%, if I remember well. And when I do the comparison, I'm having an overhead with de-risky of 3 or 4%. So they take the whole stock. So I have an overhead of I would say 8%, but on the main core. So if I take the whole stock into an FPGA, maybe it would be, I can say 1%, 2% of overhead. So I think there will not be any exceed in power consumption.
Yeah, I also think so. Maybe one more then. Let me see which one. Okay, so you use the de-risky now as an implementation platform. So I was wondering how generally applicable are your results, also looking at other processor architectures, and then I'm also thinking about, like, I don't know, different, does it make a difference if there's different pipeline depths, different architectures with respect to, I don't know, speculative execution, branch prediction? Does it all make things more difficult to implement the countermeasures that you came up with? Or?
I don't think so, because I'm only protecting the DFT registers. Yeah. So implementing a protection for the whole circuit would be probably different and more complex, but only the DFT part, as it is only the process of tags in parallel of the data, it would not be really complicated compared to this.
Yeah. Thanks a lot.
No problem. Thank you very much.
Thank you. Okay. It will be now the turn of Professor Vincent Déroule. Vincent, are you hearing us?
Yes, yes. Do you hear me?
Yes, that's fine.
Yes,
Louder.
perfect.
You can go, please.
Okay, thank you. So thank you for inviting me to review this work, and sorry to be remote. So I really enjoy reading the manuscript, and it was the same for the presentation. It was very clear, and but I have a lot of questions. So the first one is about the use of, not the use, but a comparison with classical techniques that are really often used today to protect microarchitecture. I am speaking about control flow integrity protection. I know that you are working on another specific countermeasure, not software countermeasure, but can you a little bit elaborate on comparing CFI and DFT properties?
CFI properties. CFI countermeasure is protecting the control flow of the processor, while DFT is only protecting the data flow. So DFT will protect the data coming from input source, while CFI will protect the flow of instruction, for example. So it does not provide the same, how can I say, the same protection, the different, and I'm not considering protecting the control flow. I'm considering protecting the data flow. So it's different, but there is already a lot of protection of studies for CFI against falsification attacks. So, and there was none on dynamic information flow tracking. So I don't know if it answers your question.
Yes, yes. So you mean that it's possible to use both protection simultaneously to protect a microarchitecture?
Exactly.
Okay, okay. Thank you. I have also a question concerning the countermeasure you used. The question is, does the countermeasure protect also the combinational part?
Can you repeat, please?
My question is about your countermeasure.
Yes.
We know that the laser fault injection can both impact the combinational part and also the register. And so my question is, do your countermeasure also protect the combinational part, not only the register, I mean?
No, only the registers. I'm only protecting the registers. So if the attacker is able to perform a fault inside the logic directly, there could, for example, if he is able to perform a fault, for example, into the logic of the decoder of the encoder, it will be a success for him probably, because there is no protection on the combinational logic.
Okay. I think this is an issue, yeah, because I think both fault can appear. One impacting directly the register, and other impacting the combinational logic. And it exists previous works which shown that the propagation into the combinational logic drive to a fault into specific set of flip-flop.
Okay.
Did you look at this fault model for laser fault injection?
Not at all, no. We
No.
only consider DFT related registers, and so registers in general for DFT, and no the logic. But it would be, for example, a good thing to experiment as a perspective, for example.
Yes, I think so, because it exactly it can help you to select the set of flip-flop you need to protect with parity group. And so it will provide you a way to select your parity group based on the fault model of the laser fault injection.
Okay.
So it will be nice to. Let me see. Yes, I also question. I think Bettina already asked a question on FISA, but I have another question also. So I am wondering if in your implementation of FISA, you implement specific solution to improve the fault simulation time, because of course, when you have so many faults to inject, if you do no improvement, you will have to compile all the faults. You will have to simulate all the clock cycle for each fault. It will take a lot of time, and so I would like to know if there are some improvements inside your FISA architecture to avoid some useless simulation, clock cycle, etc.
On my implementation of FISA, so there is some different end statuses that detect how to react. And for example, for my case, I have implemented a success end status. And so when there is a success, so it means that the DFT has been bypassed, the simulation is stopped directly. I don't wait for the rest of the attack window. I'm stopping directly when there is the success. Yeah, exactly. Otherwise, if there is no successes, I'm stopping at 100 cycles after the beginning of the attack window.
But for example, for each fault, do you need to recompile the design?
There is no. I'm just only restarting the design, not the compilation. I'm just only restarting. So I think the results of each fault was around for the buffer overflow, for example, it's around 0.6 or 8 seconds for each simulations. So it's quite rapid, and it will depend on the hardware used for the CPU and the rapidity and the speed of the memory. But there is no more improvement. I did not more improvement on that.
But you do not recompile, so I assume you use model sim command like force command to force a fault injection. Okay.
Yes. And I'm restarting with restart command.
I understand. I have another question about the overhead of your protection. You mentioned that your overhead is quite low, but if you only consider the DFT component, did you compare your overhead with, for example, a duplication of the DFT component? Because DFT components is probably very small comparing to the whole architecture. And so I am wondering if finally duplicating the DFT is not the same order overhead than your solution.
For that, the DFT-related registers they are 55 DFT-related registers, and for these 55 related registers, there is 127 bits in total for the whole DFT. And for example, if I'm considering the strategy 5 for SecDed, I think you can see the slide. For SecDed strategy 5, the amount of bits in total, counting the redundancy bits, the parity bits, and the DFT bits, I have an amount of 280 bits in total. So if I'm duplicating or triplicating, duplicating would be less than SecDed strategy 5, which is the worst in terms of number of bits. But duplication will probably not be enough to correct all the faults. Triplication, probably yes, of course, but it will require way more protections, way more bits than only strategy 5. But okay. the evaluation, I did not the evaluation, but of course, duplication would be probably better, but at a higher cost than strategy 5.
Yes, and also, as you said, your countermeasure do not protect against fault into the combinational part.
Yes.
And only the register impacted. So the duplication would detect all the faults, not only the register impacted.
Okay.
Okay. A last question. It's about the feasibility of the attack. If I correctly understand, the attacker need to synchronize the malware attack with the hardware fault injection. I am wondering how difficult it is to do that, and in particular, if it exists some trigger that could help the attacker to trigger the fault injection to achieve his attack.
Yes, of course. For example, with the DFT, when the application is running, the DFT will detect the attack. For example, in the buffer overflow use case, and there is a signal that I've shown in the figure previously. And if you consider this signal as a trigger, you can detect the moment of when the exception is raised, or even you could consider the propagation of the tag. You can trigger when the tag is propagated and do a trigger on that and inject a fault from this trigger. But you would have to evaluate previously at first this execution on a board, for example, to evaluate in which moment you have to inject the fault, of course.
You mean with side channel observation?
For example, you could use side channel attacks. I did not consider side channel attacks in my analysis, but if the attacker is able to do that, it could use this way to perform the fault injection more easily.
And do you think another countermeasure could be to avoid or make this synchronization more difficult to avoid this attack?
For example, as a hardware countermeasure, we could use, for example, obfuscation. We could imagine having adding some random dummy cycles before or after maybe more before the raise of the propagation of the signal for the exception, So it will be more complex for the attacker to know exactly when to inject the fault.
Yes, I agree. Yeah. Thank you, William. And so it's the end of my questions. Thank you.
Thank you very much.
Thank you, Vincent. It is the turn now of Dr. Francesco Rezzini.
So, please. Thanks a lot for the presentation and for the work. I appreciate the fact that despite many of the work in literature, you are not considering the countermeasure as given and protected, but you are exploring the fact that also the countermeasure can be subject of attacks that should be protected too. I have some question about. You focused on in-core DFT, and that was a choice you justified quite strongly. Nevertheless, now you are an expert in the domain, and there are different types of DFT, as you showed in the beginning. What of what you have done can be used as lesson learned to apply to other types of DFT, the one that you presented, and what cannot, and why?
I presented in-core DFTs. Now, if we consider another approach, for example, offloading DFTs, as core, the second core is a wall core to protect. This time, we could use, for example, CFI countermeasures to protect the wall circuit, the wall core, I would say. And because there would not be only the different registers, but this time we could extend this approach to CFI or others, or triplication, for example, this kind of countermeasures. And if we consider this kind of approach, there was also a project a few years ago in the in Rennes with project Elle, which was the protection of dynamic information flow tracking in coprocessor. So they implemented some protection and inside it to protect it against different faults. I don't remember which ones, but yes.
Okay. Can you go again on slide 52 or 53? I don't remember.
This one.
The previous one.
This one.
So can you repeat again the concept that you want to express here in this slide?
So the figure 22 at your left presents the unprotected version of the processor against a complex fault model, which is multi-bit faults in 2 registers at 1 clock cycle. So with this fault model, we got 450 successes, and this figure presents the distribution of these successes. And what is it important to see in this figure is there is 2 lines here and 3 columns, and this means that there is 5 registers. So this is the registers which are critical in that case because they led to the majority, the biggest majority of successes. And if you look closely, I'm not tall enough for that, but there is one little box there that also lead to successes. So what I want to express with this heat maps is if you are a designer, you have a limited amount of budget. You are designing your design, you're doing your design, you have a limited budget. So maybe you will have to focus on these 5 registers to protect them at first. And after that, if you still have some budget, some money, you will be able to protect the small ones to avoid the majority of successes. But you will have, of course, to focus on the 5 first. And it's the same implementation for this one. This time there is some protection implemented, but there is still some successes, there is still some leakage, some vulnerabilities from this approach. And as the majority, if I remember well, on this figure, the majority of critical registers that led to vulnerabilities are the protection registers. Maybe your implementation is not enough or done not efficiently. So you will be able to maybe do another implementation, like, for example, this one, where you decrease the number of successes to only 66 from at first you went to 4,000 to only 66.
Okay, can you go back again? No, yeah.
This
Are
one?
the registers the same or are changed? Because I cannot see from here.
This one?
Yeah, is there any overlap between the two registers or not?
No, this is only different registers. You want? There is the.
No, that's fine. That's fine. So, what do you think that combining different type of countermeasures within the same design, like some with ending code, some with the other design, could be a good approach, or it's too complex to design, to implement, and to verify? So, even if I lose a bit of optimization, who cares? I'll just use one because it's in any case simpler and faster.
You could mix different fault model, different countermeasures. Sorry. For example, you implement an encode or segdead, and then on these protection registers, which are not protected, you can implement, for example, duplication or triplication on them, which will reduce the area overhead due to this triplication, and will be able to decrease the number of successes from this register. If I can take again this figure, this register is the register, the protection register for the register file. So if you are able to duplicate it, triplicate it, it will only take, this register is on 6 bits. So if you duplicate it, it will be 18 bits. So you only add 12 bits to protect and to avoid all these successes. So it will be a good improvement on the security. Or of course, you could imagine implement other countermeasures like BCH code to detect and correct more than 2 faults. But you can.
Another question is along the line of optimization of simulations. We have a large amount of literature about fault coverage, how to do a proper analysis of redundancy for fault, possible fault design for testing and those things. Could you use this literature, this base of literature, what is done for fault tolerance since many years, or not, and why? Like, I don't know, techniques to ensure that with a certain number of experiments, you have at least a certain fault coverage, those kind of things. Could you use it or not?
I could use my countermeasure to protect against fault tolerance. Could you repeat, please?
Yeah. Fault tolerance is a domain of our design, of our engineering, that is studied since a lot of years because we have faults naturally happens. And there is a large body of knowledge on how to simulate, how to test, to be sure that you have a certain coverage using your test, during your testing, and so on. Could you use this for your simulation to speed it up, or could totally make no sense in your domain?
We could use this coverage with a statistical approach, maybe, to avoid simulate a large number of simulations from, for example, big sense. As I said, this one will take 1 million years, but I took registers from 1 to 10 bits because there is already a large number of registers that will confirm this analysis. So taking into account tools or simulation from fault tolerance will be a good strategy as well to have an idea, a statistical approach to the number of successes out of this fault model on my design. Yes.
Okay, last question is more in perspective. If you look back 10 years ago, probably your thesis would not be possible simply because you didn't have a starting tool, RISC-V. At the end of your thesis, what if you look back, you say, I would have wished to have this thing that I want in any case to have for a future research. What is this thing that would enable your future research that you were still missing in your thesis?
10 years ago, I was in software development in university. I did software development. So I wasn't not at all in hardware development. I only did that for my master's degree. So 10 years ago, yeah, I would have liked to have more knowledge maybe on hardware development, hardware security maybe as well. And yes, it would have been a good point.
Thanks.
Thank you very much.
Okay, that's my turn. Well, thank you for your presentation. What I found very interesting in your work is that the fact you considered mixed attack, making a software attack possible thanks to fault injection. That's not so usual, so it was interesting to. I learned a lot reading your thesis, so thank you for that. I do have a lot of questions. Maybe one following Nelly's question about the fact that if we are able to inject faults into circuits, maybe we won't only target the register of the tags, but also maybe the register files themselves. To protect against fault injection, we may use also parity codes, arming codes, or SecDec code. And if you do so, I was wondering if you can include in it the register of the tags, and then the overhead will seem to be almost zero.
Yes, I could protect the register file, the whole register file. It would be only 32 registers of 32 bits. So for each register, if I take only, if I protect each register individually, it would be 32 registers of 6 bits approximately. So the overhead would be higher, way higher than actually, than currently, I would, sorry. But it would still be a good protection to protect even more the DFT and the circuit against possible fault injection attacks.
Okay. Can you go to slide number 26? I have a question related to the fault model. You considered 3 fault models: bit reset, that is resetting a bit set setting a bit to 1, and bit flip, inverting the value of a bit. And there's something I don't understand. Let's consider the TCR_Q line. You have success in injecting a bit reset fault, but no success with the bit flip.
Yes.
I don't understand why.
I will explain for that. You can see that there is TCRQ and with bit reset and bit set value, and there is TCRQ21 with bit flip. This is because on my case, if I can go back to this figure, you can see on this figure that for the security policy, which is taking into account, this is compared with the TCRQ21. So this is the way of if you flip this bit, it will provide a success. So when I say bit reset and bit set, I maybe did not do a very good explanation on that, but I'm setting the whole register to 0.
That's not one bit, that's every bit inside the register.
Yeah.
Okay.
Exactly. I didn't explain that, sorry. So it's the full register to 0, the full register to 1, and only 1 bit flipped.
Okay.
So the majority, as I said, the majority of my registers are on 1 bit. So in general, for example, this one, these two are on 1 bit. So when I do a bit reset, it's only 1 bit that is flipped.
Okay. So.
But this one, it's a full register of 32 bits. So I'm setting the whole register to 0.
So you flip every bit inside the register.
Exactly.
Something else.
But, and if I can finish with that, the thing is, when I'm doing a bit reset on the TCRQ at this cycle, it's the same, it provides a success with the TCRQ21 because it will be a bit flip on this register.
You mentioned that there exist other fault models, like the instruction skip or the instruction replay. What would be the effect of such faults with your DIFT scheme?
Protecting the DFT with, for example, instruction replay.
Yes, against instruction replay
Against
or instruction skip.
I don't know if DFT will be able to protect against instruction skip, because DFT protect against the data flow and not control flow.
Yes.
So for CFI, yes, you could protect it. You protect the system against instruction skip, but with the DFT, you could not.
It would be interesting to test maybe, because I think that this is something you could simulate with your simulator.
Yes, of course.
Relatively easily, I think.
Yes. And with the tool, it will be very, very easy to automate and to process.
I have a question. I think it is quite close to one of Vincent's questions. Can you go to slide 38? It shows the coder and decoder that make it possible to compute the redundancy bits. Okay. Vincent's question was about what's happening if there is a fault at one of the inputs. In that case, you will encode a fault and load the fault inside the register, and the redundancy bit will be consistent with the injected fault. So my question is about, you have in fact different types of registers. You have the TPR and the TCR registers that are for the policy. They won't change in the course of the execution of a program, I guess. So it means that such an attack won't happen for this register, I guess. It not only on the other registers that are involved in the propagation of the type, I guess. That's one thing. And you already answered to Vincent. But what I didn't understand well is that you mentioned that if a fault is injected inside the register, the output, in fact, is not changed. Meaning that the output of the register passes through the decoder, if I'm correct.
Yes.
Maybe you can elaborate on that.
Yes, I will come back. Just to say something before, the TCRQ and TPRQ can be changed during the runtime, because this DFT has a flexible security policy that can be modified. So you can change the value of the TCRQ and TPRQ. And so if the attacker is able to fault the register, the output will be faulted, and the faulted output will be decoded. And because of these registers, the redundancy bits and the general priority bit registers, Amicode and SecDev will be able to detect the fault and correct it in case of one, and detect and correct in case of one, and detect only in case of two faults.
Okay, but maybe there is some maybe small window of opportunity for which the attack works. If you change the value inside the register, you change how the policy is applied, how the tag is propagated. No?
If you fault into the TPR and TCRQ registers?
Yes, maybe. Or
yeah, of course. If you inject a fault into the security policy registers, the propagation and verification of the tag will be different because you change. And so this can lead to successes or maybe some denial of the fault of the bypass.
Okay. So there will be a small window of opportunity for the attacker, and then it will be corrected, of course. But maybe the attack was already successful.
No, if you fault the register, the output will be corrected. There will not be any uncorrected output.
Okay, that's it. That's
Okay.
Meaning that the output of the register always goes through the decoder. Meaning that if a register is a bit of a register is flipped, the output that goes through the decoder is not corrected.
Yes.
And the content of the register will be maybe at the next cycle corrected, but the output are not changed.
Exactly. Yes.
Okay.
It's the encoder and the decoder. It's only combinational. So if in my case we only inject fault into registers and not into combinational logic, so the fault is corrected all the time, and there is no faulty outputs that is sent into the pipeline.
Okay.
But as Vincent said before, if we inject a fault into the combinational at the decoder output, for example,
also in the decoder.
this time
maybe another perspective would be to look into concurrent error detection circuits, CED circuits,
okay.
that are designed to detect such kind of faults. And as Vincent mentioned, they are I guess this is Francisco. They are used for fault tolerance.
Okay.
Okay, thank you.
Thank you very much.
I have so many questions. Don't worry, I will spare you from them. Can you go to slide 50, please? 50.
This one?
Yes, it shows the success rate, the success attack rates.
Yes.
For different protection schemes. In case there is no protection at all, you have 450 successes. And this is for multi-bit faults into register.
Yes.
Okay. And it shows that using an encode is not a good idea, in fact, because you increase the number of successes.
Yes.
So your conclusion is this code should not be used?
No, because in this fault model, I'm considering injecting up to 11 faults in 11th bit flip at the same time. And because of Amicode is able to detect and correct one single bit fault. So Amicode will detect the fault, will try to correct it, but as I said, there is maybe 11 faults at the same time, and so it will inject a third or 12th fault, and so provide another opportunity to have another success. Yes. So this implementation, Amicode is good, but not against more than 2 faults. More than 1 fault, I would say.
Yes. Okay. So the code, in fact, the code gets confused, and he himself.
Yeah, exactly. This is the limitation of this code, and you can see it is better with no protection than with Amicode.
Yes. For this kind of.
Yes.
And maybe I have the last question is slide 52. Yes, that's the same thing. It shows that Amicode, in fact, is still working. Okay, that's all for me. Thank you very much.
Okay, thank you very much.
Well, it's a turn of your supervisor now. Kenny, maybe if you have some questions or comments.
No, I'm not going to ask the question. I have 3 years to do it. So I would like to thank you for your work for these 3 years on the complex topic, mixing hardware design, hardware attacks, software attacks. It was really complex at the beginning of the PhD to go deep in the detail of the DIFT processor, and you did it very well. So thank you for that. I would like also to thank you for the help you helped us a lot in the lab and in the team when we organized events. You always participated, and finally you I talked to Nicolas yesterday. You helped to create this really nice dynamic in the team and in the lab. So now we have a strong group of students and also colleagues, and we participate to create this dynamic. And I really want to thank you about this. And yeah, I'm going to stop here, and maybe Guy, if you want to.
Okay, so it's my turn. I have the hard job to conclude. No, it's not a hard job, actually. It's a really easy job. So first, before going to you, William, I just want to take the opportunity to thank the jury members for reviewing your work and for coming here. And I know, Vincent, you would have enjoyed to join us, but you were not able. So I really want to thank all of you. It's really interesting to get your point of view on the work, and for the questions you have asked are very inspiring, and definitely they open a lot of opportunities for extension of your work. So thanks for accepting to be part of the jury and evaluating the work of William. So now moving to you, William. Yeah, definitely. Vianney was the one who was really following your work day to day. I was, less available, so I was less involved in the day-to-day following of your work, but still I was able to meet you regularly and to see how you've been evolving since you arrived 3 years ago, and now you are presenting your work. And yeah, I see the difference clearly, where you are able to present your work with more assurance and insurance in the way you are presenting and answer the questions. So this is very, very good. It's a good evolution, very strong evolution. I also want to raise the fact, as said Vianney, you are always very enthusiastic. Each time we were telling you, well, William, can you go there and present your work at the GDA or at some different events, RISC-V events, something like that, you were always saying, yeah, of course, I'm really happy to do that. And this was very pleasant for us to have someone who is really enthusiastic about explaining his work and yeah, presenting what he's doing and also exchanging with the community. So this was very nice. And also, as you mentioned, you were able also to do something which was more for the general public. So when we told you, well, it would be nice if you can do that, you said, okay, I'm going to do it. And we were able to present your work in that specific exercise, which is not so easy to present your work in a very short time. So, yeah, that was very nice. And so regarding your work, yeah, you were very dedicated. You were very dedicated to your PhD. As mentioned, Vianney, there was some, I mean, it was a new topic for us also. We were not so much into fault injection attack when we started. So we started with Noura, which was the first student who did that first PhD students. And then we were with Ciblant. So we still have a lot of things to learn on that. We've been part of the way we are improving, and now there are more students. So now there are some students that are doing some physical attacks, which is a little bit more challenging. At the beginning, it was more challenging for us So that's why also we moved to simulation because it was the first step to get into info injection. And so you've been able to really help us also to grow in that domain in terms of research. So that was something we did together. And so it's not so easy, when you arrive in a team where they already have a strong level in the domain and you are following some work that has already been done by some students, it's not the same than when you are really digging into a new domain and what you've been doing was something like that. So I really want to congratulate you for that. Now you are doing a postdoc. I know you want to become a faculty, so I think you are on the good path. I told you that a few times. I think it's important for you to really keep in mind, always try to get some maturity, some distance about your work, because that's the way you will be able to write strong proposals. And as you want to become a researcher and a teacher, this is something that definitely you need to keep in mind. Okay. Not to focus only on the technical part, which is very important, of course, because at the end, the technical part brings the results. But you need to also take some distance of your work to have a larger view and what are the research directions that needs to be addressed. And final word regarding teaching, because also we ask you about to be involved in the teaching at the Faculty of Science, and also you did it with same thing, enthusiasm. And we had some very good feedback from the students, so they really enjoyed the teaching activity you have. So yeah, again, it's a very nice feedback from us, and I would like to congratulate you so far. So at the end, thank you. It was 3 nice years. I hope you will become a faculty, and if it's the case, I guess we have many opportunities to see us again, because the French community is quite strongly connected. So thanks again, and congratulations for your work.
Thank you very much.
I think now we need to go for a deliberation.
Yes.
So, yes.
No, this was it. Because you had a really nice speech.
Well, that's my point.
We'll come back then.
Vincent?
Oui.
Je vais donc tu peux te connecter sur le. Ah oui, bah bonjour, parce que sinon on t'a pas vu encore. Donc tu peux te connecter sur l'autre lien de délibération et puis on arrive et on se connecte.
D'accord. Tu m'as envoyé un mail avec le lien, c'est ça?
Tu as dû recevoir 2 invitations.
D'accord. Je vais pas faire attention.
Une pour la soutenance et une pour la délibération.
Ah, il faut que je vérifie ça. Tu peux
Je te le renvoyer, t'embête pas.
Tu me le renvoies?
T'embête pas.
Ah, bah, super. Merci. Merci.
À tout de suite.
À tout de suite.
Que si tu utilises est-ce que j'ai un stylo?
So it is my pleasure to provide you with a feedback about your defense. Your presentation was very clear and easy to follow, very well structured, detailed enough, and it provides a good highlight of the contributions that you made to the state-of-the-art in the field of dynamic information flow tracking and fault injection attacks. Your slides were attractive, pedagogical, including rightly chosen illustrative examples. All in all, your presentation showed a great potential for teaching. You managed to answer the technical questions that were more in-depth, as well as questions that were more broad. Demonstrated a good knowledge of the state of the art related to various topics: software attack, physical attacks, the security of RISC-V based cores, security analysis, and etc. So congratulations for that. For all these reasons, le jury unanime décide de vous délivrer le grade de docteur de l'université Bretagne Sud.
Merci. Du coup, le serment, sorry, it's in French. En présence de mes pairs, parvenus à l'issue de mon doctorat en 2024 et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats.
Bravo.
Merci beaucoup.
Congratulations.
Thank you very much.
Congratulations.
Thank you very
Well
much.
done.
Congratulations.
Vincent, est-ce que tu veux dire peut-être un mot ou bien? Je ne sais pas si tu as prévu de dire un mot à tout le monde.
Je peux.
C'est comme tu veux. Après on va libérer Vincent.
Okay. So thank you very much for all jury members to have come to this PhD defense. Thank you very much for that. Thank you for the reviewers to have reviewed my PhD. Thank you for the jury members to have come. Thank you very much for Jean-Marc for being the president of this PhD and also being part of my CSC. And thank you very much also, Francesco, for last year, my mobility. It was an amazing experience. It was a really good experience and bring me a lot of good memories. And finally, thank you very much, Vianney and Guy, for this supervision during these 3 years. It was a big pleasure to work with you and to know you too. So it was a very good thing. Thank you very much to everyone. And thank you also to the public to have come today for this PhD defense. Thank you very much.
Ok Vincent, c'est mignon, on te libère, merci encore et puis au plaisir de te voir prochainement avec nous. Et,
oui. Merci.
Voilà, pour venir te voir à Valence. En tout cas, à bientôt.
Dans les deux cas. Merci beaucoup pour l'invitation. Bravo William et puis à une prochaine. Merci.
Merci, à une prochaine.
Merci, au revoir. Bon, bah super. Je vais que tu signes pour pas qu'on oublie. Exactement. Comme ça, j'aurai toutes les signatures qui vont bien. Ok, merci. Il faut pas la date. Non, non, c'est bon, là j'ai tout ce qu'il faut. Donc ensuite, bah, dès que le rapport sera consolidé, j'enverrai tout à okay. Donc je ne sais pas si ça sera fait juste avant le cours. Okay.
Il y avait un document que j'aurais besoin, je crois. Donc on va voir ça tout à l'heure si possible.
D'accord.
Parce que j'ai un rapport de passage, un contrat de post-doc qui commence au 1er janvier et il me demande un certificat sur le gestion de la thèse. Je suis d'accord pour valider le contrat.
Tu vois plutôt avec. Je regarde avec nos.
Oui, le président du jury.
Parce que nous,
ouais.
Je vois avec nous.
Ok.
Comment tu vois les choses, parce que nous, on va pas trop traîner, parce que comme Jean-Marc se parle assez tôt, l'idée c'est qu'on aille au restaurant assez tôt. Oui. Donc, typiquement à la nuit, on va partir. Donc là, on va à 11h. Ok. Est-ce que toi ça te va? Oui, ça va aussi. Donc du coup, je viens avec vous. Voilà. Et
j'ai juste échangé avec les voitures.
Ok. Est-ce que tu veux faire des photos aussi?
Si tu veux.
Est-ce que tu veux une photo avec plaisir? Oui, alors on va parler de cette partie, mais
remettre tes slides.
Ah, ok. Yeah. Sure.
Please come on, it's just if you agree, a picture of her. Ok, super. Merci. Donc, écoute, nous, on va aller dans la section 14. Ok.
Ok, pas de souci. Parfait. Merci. À tout de suite.